Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video here, we're going to continue from where we stopped. We talked about some interesting things involving the diffusion coefficient, where based on our previous video, we looked at how diffusion coefficient relates really well with the specific cross-sectional area of our molecule, where an increase in the diffusion coefficient favors a smaller molecule more than a larger particle. And on the other side, we looked at diffusion coefficient increasing with increasing temperature, therefore hotter molecules will diffuse faster than that of cooler molecules. And the final one here is relationship between the pressure and the diffusion coefficient, and all these relationships actually come from the specific relationship between the coefficient of diffusion, which is also the diffusion constant, with that of the mean free path of the gas and that of the mean speed, where the mean free path is the average distance between one particle made with that of the other particle before both of them actually collide with each other. So we know that the diffusion coefficient is measured in meters squared second -1 to the power of -1, which is per second. And based on this, we are going to arrive at tackle this particular question. We say we should calculate the diffusion coefficient of, or the diffusion constant of, nitrogen gas at 25 degrees Celsius and at this particular pressure, which is 10 pascals. So in this particular case, there's some other things that are kind of missing here, but you will need a specific table to gather those information. Like for example, we're going to need, based on our givens, we will need the following. We're going to gather first. Hey, we need the following. Let me get this out of the way. Now, based on the givens, we're going to need the following. First, of course, we know our pressure to be 10.0 Pascal, which is the standard unit that's going to be used, and we have our temperature of nitrogen gas, which is 25 degrees Celsius. We know that we need it in kelvins, which is in this case plus 273, which will give us this value 298 kelvins. And the next variable that we need to take into consideration are, first, we need the cross-section area of nitrogen gas, and the cross-section area of nitrogen gas is around 0.43 nanometer squared. And to convert this, we need to multiply this by 10 to the power of -18 meters squared in order for we to get our value converted from nanometer squared to meter squared. Therefore, this is equal to 0.43 times 10 to the power of -8, in this case, meters squared, for nitrogen gas. And so once we have all these variables, we have other things here like the constants. We know our value for the gas constant, or ideal gas constant in this case is 8.314. Take note that it is measured in joules per mole per kelvins, and we know that the other constant, which is our K value, is around 1.38 times 10 to the -23rd. Take note that it is measured in joules per kelvin. So therefore, based on this, we are going to look for what is the required, and our required here is actually based on the question, which says we should determine the diffusion coefficient. And we know that the diffusion coefficient is represented as D, and so where D is the diffusion coefficient or constant, this will be important based on our derivation and our analysis from our previous video, where our diffusion coefficient is measured in terms of D is equal to 1/3 pi times, not pi, lambda C bar. So in this case here, in terms of our analysis, we know that based on our diffusion formula, we will need to rearrange some terms and variables to fit into the given. So where our d is equal to 1/3 of the mean free path multiplied by the mean speed. We know that our mean free path is equal to, first, in this case, K multiplied by our temperature over our pressure times our cross-sectional area, which is what we have, and also multiplied by square root of 2. And the other one here is our C, which is our mean speed, to be equal to the square root of R8 multiplied by our RT all over our pi multiplied by our M, which is the molar mass. Take note that we're using the R and the big M, not the K and the small m, because we don't have the mass of that one atom, so we're going to use our molar mass in here. So therefore, in this particular case, we are going to put these two equations here in this equation, and we are going to reevaluate what our d is going to be in terms of the givens in the question. Therefore, 1/3 will be multiplied by kt all over pressure, and this all square root of 2, and this is going to be multiplied by rc, which is all square root of 8 multiplied by rrt all over pi times the molecular weight. So take note that since we have these, we are going to put our givens in this particular equation, and we're going to solve for our d. And so our d, which is now in terms of the variables in the givens, is now 1/3 multiplied by 1.38 times 10 to the negative 23, or third. Take note that the unit of our K is in joules, and we know that joules is measured in newtons multiplied by meter, and this is all divided by kelvins, and we know that our kelvin's temperature is around, in this case, 298 kelvins, and this is all divided by our specific pressure, which is 10.0 pascals. We know Pascal is Newton meter squared, and we are going to be multiplying our Pascal, which is our pressure, by the specific given measurement for our area, which is a cross section of our molecule, which is 0.43 times 10 to the, in this case, 18, and this is measured in meters squared, and finally here is multiplied by square root of 2. So this is one part, and the other part is now the other inside bracket, which I'm going to bring that down, and the other bracket here has the square root, and in here we have 8 multiplied by r, which is 8.314 joules. Of course, is measured in Newton meter, and this is per mole. Take note that is multiplied by Kelvin as well, and on the other side we are multiplying this by our temperature, which is 298 kelvins, and this is all divided by pi multiplied by our molecular weight, which, take note, is what expressed as kilograms per mole. And so therefore we know that we forgot to explore that on our givens, but we're going to do it right here. We know that the molecular weight of nitrogen gas is 14.01 times 2, which is 28.02, and take note this, it is going to be in kilograms, therefore it will be 10 to the power of -3, and we have kilograms per mole. Take note here that newtons is expressed in kilograms per second squared multiplied by meter squared. So therefore in this part here we're going to clean this up a little bit, and we are going to express that now as kilograms. We have our meter cubed, and this is multiplied by our second squared right there. So that is something to keep in mind right over there. So therefore we're going to reevaluate our units in this case, and by cleaning up our units we'll be able to arrive at our specific variable step that would then lead us to our overall value for our coefficient. I'm saying that, hey, the unit actually matches our derived unit from our previous video. So in here, kelvins cancels out our kelvins. We have our meters squared cancels our meters squared. We have our newtons canceling out our newtons, and we are left with meters in this particular space right here. And then on inside those particular square root, we have a couple of things canceling out, like our kelvins canceling out our kelvins. We have our mole, yes, canceling out our mole, and we have our kilograms canceling out our kilograms. And what we're left with is meters squared or cubed multiplied by our second squared, or divided by our second squared. So take note here that in this case we have, oh, there's meter squared, sorry, I made a mistake over there. So pardon me, this is meant to be raised, and it's supposed to be meter squared over here. And so meter squared, because in this case we know that newtons times meter gives us our joules, and for our newtons we are measuring our mass by the acceleration, which in this case acceleration is meter per second squared. Therefore meter times meter is meter squared, and we have kilograms right there. So in this case we are left with meter squared, and as a result of that we are able to now reevaluate our d, which is now in terms focusing on the bracket including the 1/3, will give us our value to be 2.25419 times 10 to the power of -4, and this is measured in this case in meters, because we have our meters right over there. So therefore on the other side we have our bracket with a square root, and our square root here will be, take note, our constant value, which will be 474.514. Take note that the unit is meter squared over, in this case we have seconds squared. So once we have this taken care of, we are going to now reevaluate our square root first. And in this case, once we have that taken care of, our square root will have these first as the constant in terms of meters, and our square root, once it's taken out, we're going to have our meter cancelling, our squared, sorry, cancelling out for both the meters and the seconds, and the square root, and this square root is applied to this, and what we have is, in this case, and so what we have here is now our meter squared is going to be cancelling with our square root, and what we're left with is our meter, and then our seconds squared in this case here will cancel in terms of the squared, and what we're left with is the seconds. And as a result of that, once you do the square root of all the constants in this square root, we're going to have our number to be 473.514. Take note that this now will be in meter per second. Therefore our specific diffusion coefficient, yeah, is finally going to be our value. Once you multiply the constants, we have 0.10696. In terms of the unit, meter times meter gives us our meter squared, and this will be over our seconds, which is actually matching our specific unit that was expressed in this particular previous video right over here. So that is really remarkable to see how everything agrees really well with our solution, and in this solution we're able to rightly derive our diffusion coefficient of nitrogen gas at a specific temperature, which is 25 degrees Celsius, and at that particular pressure. So thanks for following me through this. I truly appreciate it. Hope you found this really informative in not only being able to understand the overview of diffusion coefficient in terms of its relationship with the pressure, temperature, the molecular weight, and also other interesting things involving the mean free path and that of the mean speed, but also being able to see how this is going to be balanced with the units and satisfies the unit based on our derivation process on our previous video. So all the same, hope you found this really informative. Hit a comment down below, let me hear your thoughts. By that way, I can talk to you all soon. Stay smart as always and believe in yourselves.